Hi, I'm Chu-En from National Taiwan University. Here I will present our work, Gaiters, exploring skin stretch feedback on legs for enhancing virtual reality experience. Haptic feedback helps users to link real-world experience to virtual reality interactions. Much research has applied this feedback to the head, body, and upper limbs to simulate rich physical properties in VR. For example, prior researchers implemented prototypes to generate textures and force sensation, or simulate the grasping of rigid object. Embarrassment is a wearable accessory for HMD that provides thermal and wind feedback. Tesla suit is a commercial VR suit that generates vibrotactile feedback on the full body. Skin stretch is cutaneous feedback useful for inducing the perception of illusory forces or delivering directional cues. Recent works on generating skin stretch feedback is used as a message on the legs, mainly address lower limb prosthesis users during walking, or exploring sensitivity to skin stretch on the lower leg. However, how to expand the benefits of skin stretch feedback and apply them to the lower limbs remains to be explored. In regard to exploring skin stretches on the legs, we conducted 2 psychophysical studies and 2 user experience studies to answer the following questions. How well can participants discriminate skin stretch distance and angles? When coupled with the very lower limb actions, what kind of haptic sensation can be induced by skin stretches? Can the stimuli increase the immersivity and enjoyment in VR? Our first 2 psychophysical studies examine the minimal changes in skin stretch distance and stretch angle that are perceivable by participants. To help us design the magnitude of the skin deformation used in VR applications, we investigated the minimal detectable change in skin stretch feedback. Considering the lower limb anatomy, we focus on 2 crucial factors of skin stretch: stretch location and stretch direction. For stretch location, considering the ease of wear, we decided to exclude the thighs and focus on the calves for this work. Previous research found that the human skin is more sensitive to the stimuli on the upper calcaneal tendon, the lower fibularis longus, and the soleus, which are 12 cm above the ankle. We also tried the front side of the calves. However, there is less muscle in the front, which often causes users discomfort. We thus test the above-mentioned 3 locations in the study. For stretch direction, based on lower leg anatomy, we choose the directions vertical or horizontal for the lateral skin deformation caused by leg muscles. In order to rule out other ambiguous feedback, we implemented a leg scale, grounded apparatus. The device was assembled with real alumina extrusion, and we implemented 2 linear actuators with belt drives on the framework. Each belt is driven by a stable motor with minimal displacement of 0.1 mm, which enables smooth 2-dimensional movements of the shear detector. We overlaid a piece of a sponge on the rest to allow participants to lean their leg on it comfortably. A load sensor was placed between the rail system and the detector. We asked the participants to adjust the apparatus until they saw the detector was stable yet comfortable to attach. The average value from the sensor was approximately 14 newtons across the participants. The shear detector for dragging skin is a concave plate with 35 mm in diameter, and is covered with 3 mm thick silicone pad to ensure the user's comfort. We conducted 2 genetic studies on stretch distance and angle on the calves. 1 up-to-down staircase method is applied in both of the studies. We assume that the skin's sensitivity on both legs is similar likewise with each pair of sample points. Our factorial design consists of 3 locations with 2 stretching directions. 12 participants were recruited, and the order of study conditions was randomized. For study 1, discrimination threshold of stretch distance. On the left is how our device works in distance journey study. The right is the control interface. We provide 3 stimuli and ask participants to select the one that is different from the other 2. Our results suggest that the change in stretch distance must be at least 14.05% higher or lower than the current stretch distance for people to perceive a difference, and that multiple levels of magnitude can possibly be generated within a reasonable skin stretch range. For study 2, we also evaluated discrimination threshold, but for stretching angle. This average discrimination threshold of stretch angles across all conditions is 14 degrees, and the highest standard value is 25.8 degrees. The results suggest that it is possible for users to distinguish more than the 8 cardinal directions according to the skin stretch feedback on a single point of the leg. Then, we designed and implemented Gaiters, a pair of skin stretch devices worn on the user's cap that perform 2 degrees of freedom skin stretch. To avoid the counterforce generated during stretching from affecting the user's perception, we integrated the modules on the cap breast. Each cap breast consists of 3 skin stretch modules. A module contains a frame, an X and Y axis, and the detector is actuated by 2 gear motors. One is used for horizontal movements and the other for the vertical movements. In this exploratory study, we test action coupled profiles to understand how to utilize them to induce the different types of perceptions. The participants were asked to experience each pre-made stretch profile while performing an assigned action, which were designed based on leg action and skin stretch profile, and then report their experience and agreements with the perceptions we evaluated in the study. Based on prior research, the perceptions evaluated in this study include pulling force, weight, rotational force, and friction. 10 participants were recruited in the study. The stretch profile was experienced when participants performed standing, walking, and kicking actions. 6 stretch profiles were tested, including upward, downward, leftward, rightward, forward, and backward. For pulling force, the results suggest that for standing and walking actions, generating downward and backward skin stretches can induce pulling sensations. For sensation of weight, when participants were standing or walking, generating upward or downward stretches induced a change in the perception of body weight. For frictional force, participants show high rates of agreement on which skin stretches represent frictional forces. For rotational force, when standing still, most of participants could sense clear rotational forces from leftward and rightward skin stretches. According to our previous results, we implemented 2 applications to demonstrate Gaiters. First, horror escape game. The users were asked to explore in the dark and find a key to escape from an abandoned hospital. We select stretch profiles that were found to be effective in the exploratory study. 4 profiles were used in simulate the sensation of grace by something, pulling force, weight, and water flow. For fancy go game, we simulate impact and acceleration force. These perceptions were reported by the participants in the exploratory study. We use 3 profiles for the 3 types of kicking action: normal shot, curve shot, and power shot. Each shot can be activated by a certain body posture. We conducted a user evaluation study for the applications. This study is designed to measure the user's subjective feedback on Gaiters in comparison to use without haptic feedback. They were asked to use a continuous 7-point Likert scale for agreement rating on their feeling in regard to realism and enjoyment. For horror escape game, the results indicate that all the skin stretch profiles received significantly higher scores than the non-haptic condition. 3 participants reported that the pulling sensation was realistic and helpful to understand the urgent situation. However, there were 3 participants that gave lower scores rating for weight and water flow profiles. They saw the area of skin stretch should cover both my legs completely as the water was above my knee. For Fancy Go Game, the results indicate that for both realism and enjoyment compared to the non-haptic condition, all skin stretch profiles received significantly higher scores. One user said that the directional cues from the legs helped me to feel the path of the ball, which increased immersivity. And one participant suggests that for the curve shot, the realism could be higher if the stretch distance is larger. All future work includes examining more factors such as the size, shape, and stretching speed of spectators. Also, the gender values were examined under standing condition. More body conditions such as walking and kicking explored in the exploratory study should be tested in the future work. To the best of our knowledge, also Gaiters are the first wearable device that generates 2 degrees of freedom skin stretches on the human calf. The weight and size of Gaiters are larger than other one-dimension skin stretch devices on the lower limbs. Future work will focus on improving the hardware design and minimizing these 2 factors. It would be also interesting to place the skin stretch device at other unexplored parts on the body. The contributions of these works are: first, creating lateral skin displacement by physically stretching the leg skin. Second, user study results that investigate the capability of skin stretch on leg surface. Third, implementation of Gaiters, a proof of concept prototype. Fourth, a set of applications that demonstrate that concept. And the results of a preliminary user's evaluation of this new haptic prototype. Thank you for listening.